All right, everyone. So now we are going to get into lenses. So we're going to talk about some of the similarities, differences between lenses and mirrors, and trying to figure out how to draw a ray diagram to identify where an object is going to be viewed if we have it passing through a specific lens. So here are our two different types of lens that we're going to see. We use pretty similar naming for each one of these lenses as we did our mirrors. So this lens here is what we call a converging lens. And this one here is a diverging lens. Now, sometimes these are otherwise noted as being a biconvex lens or biconcave. Right, and really that is just saying that there are two individual lenses that are convex lenses, and they are going to kind of lead to the properties of being a converging lens or a diverging lens. So really, just to put it quite simply here, with our converging lens, if we're having parallel rays coming into that individual lens, right, they end up going to be directed back towards that principal axis, right, which ideally here would be our focal point. Whereas a diverging lens, as those rays pass through, they are going to be moved away from that individual principal axis, and it will be actually using the individual focal point before it. So when we look at these, right, these are going to kind of follow a little bit of a different mechanism than when we look at our mirrors. So I'll quickly here kind of compare the first type of lens that we're going to be looking at is our converging lens. And I just want to quickly compare that to a converging mirror and kind of see where the similarities might lie. So if we look here, we have a converging mirror. We know from kind of our past experience that if we have this converging mirror, we are going to see that each one of these incident rays, because they are running parallel to the principal axis, are going to be reflected back through the focal point. So really, if I were to take all of these rays, they're all going to end up reflecting directly back through that focal point. So again, if we really want to look at this in depth, right, all of those individual rays are converging at one point. So again, that's really where we get that word converging from when we are talking about these mirrors. Now, when we start talking about the converging lens, it works pretty much on the exact same process, right? If we have parallel rays coming in, or sorry, incident rays are parallel to that principal axis, again, those individual rays are going to converge at one point. But instead of now reflecting back to our focal point, right, they're going to continue onwards to the second focal point, which is going to lie beyond the lens itself. And we are going to see that as these pass through, again, those individual rays are now going to converge on our second focal point. However, I do have a couple of other rays coming here, showing that they are coming directly through. So these are incident rays as well. They're coming directly through our focal point on our side of the individual lens. Now, if we look at those ones, as you might expect, very similarly to if we had a individual ray passing through the focal point on a mirror, those rays are going to just pass through that mirror parallel to the principal axis on the opposite side. So really, we're starting to see that there are quite a few similarities on how a converging lens is going to work in comparison to a converging mirror. Right? Still, when we are having parallel rays, they're all going to converge at one specific focal point. However, in this situation, instead of that focal point being on our side of the mirror or on the real side of the mirror, they're going to be focused on the back side of the mirror, or the lens in this scenario. Okay, so just kind of a quick little breakdown, and we'll talk about the rules a little bit later on before we get into our ray diagrams. So really, the big thing that we're going to talk about here is the difference between reflection and refraction. And refraction is actually a term that you have seen before. So reflection, right, we look through some pretty simple gizmos and things like that, talking about the ideas of reflection and how reflection works. And we know that there are some pretty simple properties that we follow, especially if we're looking at, say, just a plane mirror here that we're seeing down below, right? We know that this here, our angle of incidence, is going to equal the angle of reflection. Now, when that is happening, right, essentially those light rays are just going into that surface and reflecting directly back towards the viewer. Okay, so the incident rays reflect off of a mirror and return to the viewer, which is you. However, refraction works a little bit differently. And we saw this when we started looking at prisms at the start of the unit. Now, when we start talking about refraction, oftentimes we use the term bending. So refraction is really the bending of light when it passes through some transparent medium. So that medium might be glass, it might be air, it might be water droplets in the air around us, it might be some sort of a prism. But really we're talking about the bending of that light, and we know from our past experience that that is not actually really bending, it's just that light slowing down and then speeding up again as it passes through that prism. So in the example that we saw in our video at the start of the year, that light was passing through. And if we talk about those wavelengths of light, say red light, we looked at it as being kind of these vertical lines. But as this vertical line is going to approach or hit the side of the prism, if it is halfway inside of that prism, this bottom side of that that wave, is going to be slowed down where the top side is still moving at its original speed. And what that's going to happen to do is, if we have our pen here, if I come and I slow down the bottom side, I'm going to see that my pen is going to tilt. So instead of continuing on in the same direction, right, that is going to slightly tilt down and the angle is going to be adjusted. And then as it comes out of the other side of the mirror, we can again look at our pen example, imagining that the bottom is still being slowed down and now the top is speeding up, right? And that is going to cause that to bend even further as it is coming out of the other side of that prism. So if we look back at our individual lenses, the same thing is happening, right? If we look at a parallel ray coming into the front side of a converging lens, as those rays are contacting the front side of that lens, the bottom of that ray is going to be slowed down, whereas the top is still moving at the same speed. And what that's going to do is that's going to cause those rays to be tilted downwards. And then as they come out of that individual lens, they're going to now speed up the top side while the bottom is still slowed, causing them to bend even further. So that is really where we are getting that individual refraction or that bending of light when we are going through that mirror. And the same thing would work as if we're going through a diverging lens. As these individual light waves are passing through, at this point now, the top is going to slow down where the bottom is going to continue moving at the speed as it is passing through the air. And it is going to start moving in an upward direction. And then as those individual light waves come out of the other side of that mirror, right, the bottom is going to now speed up, whereas the top is slowed down, causing those to tilt up and be diverted away from the principal axis. Okay, so that really is kind of the breakdown of how these two lenses are working. So now kind of understanding the difference between reflection and really what refraction is, we're going to kind of move on to actually looking at these specific lenses. So when we are looking at our individual converging lenses, again, we are going to have three rules. And these rules that we're going to follow when we're creating our ray diagrams are going to be quite similar to the rules that we saw when we were working with mirrors. Now, the first rule that we are going to see here, and I'll do that in green, is talking about when we are going to have parallel lines to the principal axis entering that lens. So when parallel incident rays enter the lens, we can see that they are going to be refracted, and they're going to be refracted through our focal point. So if I were to draw a incident ray coming from the top of my arrow, just as we did in our other examples, coming parallel to the principal axis into this individual lens, we are going to see that that is then going to be refracted through the focal point. Right, so we're going to continue this ray down through my focal point. Okay, so now this is not going to be called an incident and a reflected ray. This is now going to be called an incident ray and a refracted ray. Right, so really the exact same process, but instead of reflecting back through our focal point on our side of the lens, we're now going through a secondary focal point. And when we start talking about a primary and a secondary focal point, oftentimes what you will see in our examples is we have these little symbols up here. And really what these are is what we call prime symbols, right? So we have F prime, and that is going to be the focal point on the object side of the lens. And then F prime prime, or F2 prime, is going to be the focal point on opposite side of the lens. Right, so really we just use those to denote the difference between this one and this one. However, if you were to take a ruler and to measure the distance from each one of these to our kind of center point of the individual lens, you'll notice that each one is approximately 3.8 centimeters away. So they're the exact same distance away from that individual lens. They're just on opposite sides. Okay, so that is rule number 1. Now what we are going to see next in this rule is a little bit different than what we saw before. So this one being in black is talking and saying that when light passes through what we call our optical center, right? So this here is what we call our optical center. And what we will notice is that if light passes through the optical center, it will not refract. Meaning that it is going to continue directly through that lens without altering its pathway at all, right? So if we were to kind of draw a line to represent that, if I have a line from the very top of my arrow directly through that optical center, we are going to see that that line is going to continue onwards without any refraction, right? And if we think of that kind of back when we look at our lenses, that does make sense to us because really the angle that it is coming into this lens, it is leaving at an opposite angle on the other side. So if we were to have it kind of passing through here being the optical center, and I had it passing kind of along this direction here, I'm going to see that if I had these light waves coming in, again, using my pen example, right, the top of the pen is going to slow down before the bottom of the pen does. And what that's going to do is it's going to kind of allow those light rays to pass a little bit higher. But then once they come out, the top of the pen is going to speed up and they're going to correct themselves back on that exact same pathway, right? So if they are passing through that optical center, kind of following the same rules as if they were to pass through the center of curvature, we are going to see that there is going to be no variation in that individual ray. And then finally, our third rule is going to look and see that if we have light passing through F prime, which is right here, which is our focal point on our side of the lens, we are going to see that then it is going to reflect parallel to the principal axis. So if light, or if our incident ray passes through F1, or F prime, sorry, then it will reflect parallel to the principal axis. Right, and just as a quick little side note, the focal point that I mentioned up here is going to be F2 prime, or F prime prime. Okay, and that is this one here. So this one is now talking about our focal point on our side of the mirror. So if we have a ray that is passing from the top of our object down through the F prime, imagining that this was a little bit extended, if it passes through that F prime, then it is going to reflect parallel to the principal axis. Okay, so those are really our three rules. These rules don't really differ too much from when we were looking at mirrors, right? Really, the overall process is going to be the same thing. Again, we're just looking at those individual focal points and trying to use those as a reference point to figure out where those individual lines are going to converge a little bit later on. So now moving on, what we are going to see is now an example on how are we going to create a ray diagram using these rules. So again, if we go back, our very first one is going to say that if we have an incident ray traveling parallel to the principal axis, it is going to be refracted through F prime prime or F2 prime. So we are going to do that process now in our example. So I'm just going to take my ruler, right? I'm going to try and draw as parallel as possible line from the point of my arrow to the center mark of our individual lens, right? So oftentimes on every single one of your examples, you will have a center line indicated on that lens. So again, this here is my incident ray. Now, given our rules, we know that that incident ray is going to be refracted through F prime prime or F2 prime. So I am now going to take a mark from the very center of that lens, right? And we are going to refract that down through F2 prime, and you're going to extend it pretty far beyond that point, okay? So I'll just kind of show this down here as being my refracted ray. Now that there being a refracted ray, okay, that is done for right now, okay? Really at this point in time, we are going to be looking for the point where all three of these individual rays are going to converge, okay? Now if we go back to our rules, our second rule is going to say that if light is going to pass through the optical center, then it will not refract whatsoever. So our second rule, we're going to take our black marker, we are going to go from the point of our object through the optical center and continue that line onwards as far as possible. So here I'm going to draw this here directly through, right? So that is not really going to be any bit of a refracted ray, right? This is just going to remain as an incident ray. Okay. And then finally, our third rule is going to tell us that if our incident ray passes through F prime, it will then reflect parallel to the principal axis. So for our third one, we are going to go from the point of our object again down through f prime, which is this object here, or the focal point on our side of the lens. We're going to start at the point, go down through there, and again, we are going to stop once we hit this point in the center of that individual lens. And then we are going to continue that line on parallel to the principal axis, or as parallel as possible. And what you are going to notice here is that all of our rays are going to converge at one specific point. Right? Now this point here is going to be the location of the tip of our arrow on the opposite side of the lens. So again, this here is an incident ray. I really should be including my arrowheads to show the direction. So this is incident, and this here is refracted. So again, remember not to use reflected. These are going to be refracted, right? And then the exact same thing as any of our other ray diagrams when we are given something like an arrow, right? The point where all of these are going to converge is going to be the point that you are referencing on the other object. So looking here, that is going to be the point of the arrow. So that would be the point of the arrow there. And then we will see that the base of our arrow is going to continue upwards to our principal axis. So if we look here, right, just talking about our individual lenses, we are going to see here, if we were to talk about our salt, our size, attitude, location, and type, right, we are going to see that if we were to start on the center of curvature, which is the first example here, right, we are going to see that the size, if I were to measure these two objects, so if I go here and measure my first arrow, it is going to be approximately 2.5 centimeters. And if I measure the second arrow, it is also exactly 2.5 centimeters, right? So this was actually a very well done ray diagram. So using that information, right, we can see that the size, if the original object is going to begin on C, or the center of curvature, or 2f prime, we are going to see that the size is the same. Now, if we look through, right, remembering our attitude, we either have the option to be upright or inverted. Now we can see here that on our object, it was pointing upwards, whereas our individual image that we created, it is now pointing downwards. So this, the attitude of this would be inverted. Now, if we look at our location, right, it is going to be located on the center of curvature, but on the opposite side of the mirror, right? So this would be, if we're looking at this as being F2F prime, this is going to be 2F prime prime, right? So our location, right, is the center of curvature, right? Or we can otherwise denote it as that as being C prime prime or 2F prime prime, right? So that's just telling us that it is going to be at the center of curvature that is beyond the mirror and not on the same side of the mirror. Now, if we are talking about type of image, and this is going to be where it is a little bit different from when we are talking about our mirrors. When we are talking about converging lens, or so any lenses whatsoever, we are actually going to kind of do the opposite as what we would see in our mirrors. Okay? Instead of having our real images being on the same side as the object and our virtual images being on the opposite side of the object, it's actually going to be vice versa. So anything that is on the opposite side as the object is going to be what we call a real image. And anything that appears on the same side as the object is going to be a virtual image. And that is just because when we are looking at this object, these light rays are not reflected rays, right? They are the original rays that have just been bent or moved to converge over on this side of the lens. So really, this is going to be a real image, right? And we'll see a little bit more detail on really why the difference between a real image and a virtual image are flipped in comparison to the mirrors that we looked at earlier. So this is going to be a real image. So on your worksheets now, you are going to have a variety of different situations where you are going to complete these ray diagrams. So using these ray diagrams, what I want you to do is you will be given various locations where your object will be located. The one that we did here in this example, the object was located on the center of curvature, or C prime, or 2F prime, right? But in the other situations, you're going to be given one location where it's beyond C, one where it's between C and F prime, one where it is on F prime, and one where it is in front of F prime. And what I want you to do is complete those, and then afterwards you are going to complete a salt table just like this one. Now, one thing I want you to keep an eye out for is that when you are completing these individual examples, you may run into some problems, right? And I do want you to note that if something isn't working, don't sit there and struggle with it, okay? Try and go through. If it doesn't work or isn't really making sense, okay, move on from that problem and move to the next one. And after you are done everything, you'll probably be able to find one or maybe two specific issues that you can comment on afterwards, and it'll make a little bit more sense in the end. Okay, so good luck with those. And then our next lesson, we will talk about diverging mirrors and diverging lenses.